energy-conscious housing. In Saskatchewan, work started in 1979 on 14 houses with the goal of reducing space heating requirements to less than 50 kilowatt hours a year for every square meter of livable floor area, which is 1/10 of normal requirement. These houses are called low energy, super insulated, or super energy efficient. These terms denote the high level of energy efficiency that is aimed for. The techniques of envelope construction used successfully in Saskatchewan, and shown here, are still evolving and do not constitute final answers. They should be taken as examples and not as guidelines. The secret of energy-efficient housing is that almost 1 of every 2 watts of total energy needed to heat a relatively well-insulated house comes from the occupants, their appliances, and the energy gained from the sun. So if the total energy lost through the envelope of the house is halved, practically all heating needs can be eliminated. Some built examples show that at 1981 fuel prices, the energy savings of these houses is outweighed by the additional construction costs. An energy-efficient house is not a short-term investment. It's an excellent insurance against future fuel price increases. Let us start with the principles. The 4 main principles of energy-efficient housing are high level of insulation, airtight construction, controlled air supply, and passive solar design. The first principle of energy-efficient housing is high level of insulation, which reduces heat losses through the house envelope. These 3 section drawings show the relative envelope thickness for traditional housing complying with the 1978 energy measures developed under the auspices of the National Research Council, and energy-efficient housing. The basement insulation in traditional construction ranges from none to RSI 1.2 for a depth of 600 millimeters below grade. In the energy measures, RSI 1.6 is recommended. Energy-efficient basements typically have RSI 2.8 to 3.6, preferably placed on the outside. Similarly, the wall insulation is also much greater than in traditional housing. In fact, the wall insulation levels can vary from RSI 5.3 to RSI 10.6, depending on the local climate. Insulation in the attic is increased from about RSI 3 in the traditional house to RSI 7.0 to 10.0 in energy-efficient housing. This is substantially more than the RSI 5.6 of the energy measures. This means that the thickness of the attic insulation is at least 300 millimeters in energy-efficient housing. These high levels of insulation are of little effect unless attention is paid to the second principle, airtight construction. A well-sealed air barrier is essential in increasing air tightness. In the examples that follow, the vapor barrier is used also as an air barrier, and air tightness is achieved by improving the details of its installation so that it can act as a sealed envelope. This calls for careful workmanship wherever there are intentional holes or joints in the barrier. A vapor barrier installed with this level of care is called an air vapor barrier. It reduces infiltration heat losses and reduces the risk of moisture damage arising from movement of the interior humid air into the walls and attic. The flow of moist air through the envelope of a traditional house is reduced by the combustion furnace, which forces the interior air up the chimney, causing slightly negative pressure. In energy-efficient housing, either because a chimney is not needed or because the furnace operates less often, moisture can accumulate within the house. If this moisture finds its way into the house envelope, it can reduce the thermal resistance of the insulation, or worse, it can cause drastic deterioration of the structural frame by rot. An air vapor barrier is an essential safeguard against this. Air tightness tests can be used to estimate air leakage and the effectiveness of the air vapor barrier. Sweden already has a standard for air tightness, and Canada may have one soon. The third principle of energy-efficient housing is controlled air supply, used to maintain air quality. Furnaces should have their own combustion air supply. A heat exchanger is often used to recover heat from exhaust air. The fourth principle, passive solar design, can substantially improve the performance of a house by placing windows to take advantage of the sun's radiant energy. It is a cost-effective measure, but careful judgment is needed to choose window sizes and location. Having examined the principles, let's now look at each element of the envelope. The placement of insulation, the location of the air barrier, and the reduction of thermal bridges at junctions are of special concern in energy-efficient housing. Foundation walls and basements are a significant element for heat loss because of the action of ground moisture and the large thermal storage capacity of the earth. It is preferable to insulate concrete foundations on the outside by attaching board types of insulation. Exterior insulation protects the wall against harmful temperature swings. The insulation should be carried to the footing. In pressure-treated wood foundation, bad insulation should be installed within the frame. Fixing the insulation to the exterior with adhesives may not be very successful. Systems are being developed for insulation attachment to foundations. Special products are available to fix additional insulation to the inside of the foundation wall, but a conventional stud wall is also suitable. Good drainage is always essential, and for most locations, the provision of a slip coat of polyethylene placed in front is necessary to stop damage to the insulation. Above ground level, the insulation is normally protected by parging on wire lath fastened to the concrete foundation through the insulation. Unheated crawl spaces can be insulated by using insulation to the depth of the joists, held in place by chicken wire, or sheets of chipboard or plywood on flanges nailed to the bottom of the joists prior to their being laid. Alternately, the crawl space walls can be insulated and any crawl space vents closed in winter. Energy-efficient housing pays special attention to the junction at the top of the foundation wall. Normal construction sets the joists on a well-anchored plate and places insulation in the joist space, but it is difficult to seal around the joists. A large amount of air leakage occurs at this point, and condensation can often result. Energy-efficient housing runs a considerable amount of insulation on the outside of the header, up to RSI 3.6. This reduces the likelihood of condensation on the warm side of the header. This technique also reduces the thermal bridging caused by headers and wall plates. The air vapor barrier can then be put on the outside of the header. This differs from normal construction practice in that the 6mm polyethylene has to be placed during framing. Care must be taken that it is not damaged. Cantilevered floors should be packed with insulation. The air vapor barrier from the wall above should be continued across the floor to the top of the supporting wall. Rigid insulation should be tightly fitted between the joists and sealed with caulking to maintain the airtight construction. Traditional stud walls, even those 140 millimeters thick, do not allow the levels of insulation required for this type of housing. Therefore, a second or even third layer of insulation is added, which not only increases the thermal resistance, but also eliminates thermal bridges caused by wooden studs and plates, which have low thermal resistance compared to insulating materials. This second layer can be either on the inside or on the outside of the structural wall. It can even form a second wall with a space in between. These multi-layer walls make it possible to install the vapor barrier well inside the wall construction, and hence reduce the risk of damage from electrical installations or the installation of drywall. It is important that the vapor barrier is positioned so that at least twice as much insulation is on the outside as the inside. Where a second wall is not built, some rigid insulation is generally fixed to the outside and carried down the wall into the ground. This cannot be too thick, or it will make fixing the siding difficult. This rigid insulation could act as a second vapor barrier, which requires that the inside space be allowed to dissipate moisture if there is a leak in the air vapor barrier. Insulation is often added between interior 38 by 63 millimeter horizontal strapping to create less thermal bridging than simply a thicker stud. This also allows electrical wiring to be more easily laid in front of the vapor barrier, which is run between this insulation and the main wall. Ceiling insulation should be tightly fitted between truss cords to minimize air pockets under the insulation. In energy-efficient housing, there is a slightly increased possibility of truss lift. This is believed to be caused by temperature differences between the top and bottom cords. Systems to reduce this effect are being developed. The increased weight of insulation may cause the ceiling plasterboard to sag if it is not installed according to the manufacturer's recommendations. Traditional cathedral ceiling rafters can seldom accept the increased thickness of insulation, often about 400 millimeters. Trussed rafters that accept the greater thickness are now available. Ridge or gable vents should be sized according to standard practice. The insulation in the ceiling of energy-efficient housing is deeper than in normal housing, so that the insulation stops need extra attention to keep the ventilation clear at the eaves. The roof trusses can also be designed with higher heels to permit high levels of insulation at the top of the exterior walls. We will now turn to other building details. Windows are a source of energy loss, not only because of the low thermal resistance of the glass panes, but also because of air leakage around the openable and fixed frames. Several novel techniques for reducing heat loss through windows at night have been tried, including the filling of the space between glazing layers with polystyrene beads. Sealing the windows is best done by installing some of the air vapor barrier before the window frame is fixed. Staples and sealant bond are then fixed to the main air vapor barrier after the insulation has been installed. Double glazed windows on the south side often contribute substantially to heating through solar gain. Windows that are not facing south should preferably be triple glazed, as they generally lose more heat than they gain. Doors present the same air leakage problems as openable windows. The door frame should be prepared using the same technique as for windows. Thermal doors are often used in energy-efficient housing. They are typically RSI 2.1. Some of these houses attempt to use south doors for solar gain.